In this lecture, we will see some fields of low temperature research. We will investigate four research fields. That is, the superfluid transition of the liquid helium-4 confined in the finite system, the superfluid transition in liquid helium-3 and helium-3 and the helium-4 mixture, the superconductor transition and nuclear magnetism and nuclear spontaneous ordering behavior. Let's first phase transition in confined liquid helium-4. Data on the specific heat, superfluid density, and thermal conductivity of the bulk liquid helium-4 supported theoretical prediction of the critical phenomena in the system of thermodynamic limit, such as the critical exponent, scaling relationship, and the amplitude ratio. The correlation length, the only measure of the distance at close to critical point in this three-dimensional system, is larger than the system size in all directions. The correlation length in this case represents the distance that the fluctuation spans. This length diverges close to the critical point T lambda, but is a few angstrom away from it. Due to the infinite correlation length near the critical point, a fluctuation that originated at one location in the system can spread to all other locations, disturbing the system's order and causing the transition from superfluid to normal fluid. At the T temperature, close to the critical point T lambda, the correlation length is given as this equation. Here, chi 0 is about 3 angstrom. The critical exponent mu is 0.6705, and the reduced temperature is represented by T as this quantity. The finite size effects can be observed if the correlation length is close to the system's dimension. The low-dimensional behavior also appears when the system's dimension is significantly smaller than the correlation length. Thus, dimensional transition behavior can also be observed at or around the critical point if the spatial homogeneity of the system is sufficient. Let's see the superfluid transition in a finite system of liquid helium-4. The system in between two-dimensional and three-dimensional systems is referred to as the finite size system. The size of the system in a two-dimensional system is only a few atomic layers, which is significantly smaller than the correlation length. On the other hand, in the system of finite sizes, towards the critical point, at least one dimension becomes comparable to the correlation length. Due to the effects of finite size and transition from 3 to 2 dimensions, the missing signals can be seen in the specific heat and superfluid density data of this finite system when compared to those of three-dimensional system. So you can see here this is the specific heat data, and the lambda point is here, and bulk data is shown, red line. It diverges at the T lambda. However, for confined system, as represented by the blue line, so we have some missing signal between bulk data and finite size system data. This figure shows fluid density data, and red line represents bulk data, and blue line represents the confined system data. So also here we can see the missing signal between bulk system data and confined system data. So missing signal in specific heat and fluid density data in the finite size system. According to the finite size scaling theory, this missing signal is scaled with the confinement of the liquid helium. Even in non-uniform thin films, the critical phenomena differ between systems of finite size and those with 3 dimensions. The interpretation of the results of experiments in this case is rather difficult. We must contain the liquid helium within the well-defined space in order to test the finite size scaling theory. The well-defined space's size can also be systematically controlled due to the difficulties associated with making a well-defined space, eliminating the Wall effect and the small signal. It is difficult to obtain experimental data to verify finite size scaling. Here, we may disregard the Wall effect and other effects observed in other finite systems if we use the confined helium to test the finite size scaling. Particularly, precise measurements of the physical properties of the bulk helium system allow for exact determination of the missing signal in the finite sized system. Making a well-defined confinement in which to place the liquid helium is thus important. Now let's see the fluid transition of liquid helium confined in silicon cells. A semiconductor lithography technique was used to make silicon cells with well-defined components. The lithography technique was used to make the SiO2 spacers here on one of the silicon wafers. Then this wafer of SiO2 spacers was bonded to the other silicon wafer through a fill hole. This fill hole, liquid helium was introduced into the empty space between two silicon wafers. This space. To observe the fluid transition, a silicon cell was mounted to the torsional oscillator unit here. This yellow figure shows torsional oscillator in one piece, made in one piece. By varying the height of the SiO2 spacers, several cells that had different confinement sizes were formed. Okay. The confinement size is determined by the height of the SiO2 spacers. The silicon wafer should be exceptionally flat to ensure homogeneity of confinement size. Due to the decreased momentum of inertia caused by an increase in superfluid density with a lowering temperature, the period of the torsional oscillator, expressed by this equation, decreases with a decreasing temperature. That is not temperature, that is period of the torsional oscillator. I is momentum inertia of the torsional oscillator, and K is spring constant. The oscillator's period change in response to temperature is extremely small. As a result, the silicon cell's own inertia, momentum inertia, and its own momentum inertia should be as small as possible. The silicon wafer should have the smallest thickness possible for this purpose. Therefore, the silicon wafer for the cell should be manufactured to satisfy those specifications. That is, thin enough but as flat as possible. So the two conditions should be satisfied for silicon wafer. Using a Fabry-Perot interferometer, the confinement size was determined. Measurements of this confinement size at 30 different spots on the cell revealed under 1% inaccuracy. By varying the height of the SiO2 spacer, a variety of confinement sizes could be formed, and the finite size scaling theory could be tested by making systematic measurements of the superfluid transition as function of confinement size. One piece of beryllium copper was used for fabricating the torsional oscillator unit. This is a torsional oscillator unit. This unit is made by one piece of beryllium copper. This torsional rod, torsional rod, has a Q value that is exceptionally high, roughly 10 to the 7. The torsional oscillation is caused by the capacitive force applied to one of the electrostructure wings, and the other wing detects the oscillations signal to calculate its period. So one of this oscillator wing will apply capacitively a force for oscillation, and in the other opposite side we detect this oscillation to determine the period of the oscillation. The oscillator's period alters in response to changes in the superfluid percentage of the liquid helium as function of temperature. The missing signal of the superfluid density of the confined helium, or this value, that is bulk value, and that's finite system value. Near the superfluid transition temperature is scaled as a function of this. So L is here. L is the confinement size. Mu is the correlation length exponent, and small t is the reduced temperature, respectively. The exponent of the three-dimensional system can be used for the finite system according to the theory of finite size scaling. The torsional oscillation is caused by the capacitive force applied to one of the electrode structure wings here, and the other wing detects the oscillations signal to calculate its period. The figure shows the superfluid density for four different confined sizes as a function of temperature. The solid line in the figure represents the bulk superfluid density for the bulk system. So this line represents the superfluid density for the bulk system. It is evident that the superfluid density is deviated from the bulk value close to the phase transition temperature. So here, on here, so from start from here, deviated, here, deviated. Okay, you can see the deviation of the superfluid density from those of the bulk system. The multiplication factor was applied to data for each confined size in the figure in order to distinguish between the data for the various confined sizes. So we multiplied some values to distinguish between the data for the various confined size. Data for 3.9, 2.8, 0.106 micrometer sizes. This one and this one. We multiplied by 2.5 to distinguish the data. This is a picture for the silicon cell and torsional oscillator system. That is the electrode for apply force to the wing of the torsional oscillator, and in opposite side we have another electrode to detect the signal, and we have some temperature controller system here, and here we have a helium pot. The missing signals, this value of the four different confined sizes are plotted as function of d to the 1 over mu t in the upper figure to test the finite size and scaling theory. All data should be collapsed onto a single line if the data is scaled with a scaling function of this function in accordance with the finite size scaling. However, the data are not scaled by the function of this function, as can be seen in the figure. The missing signal data was scaled in the lower figure only as function of the reduced temperature T. This has been tested, since we might assume that the variable d to the 1 over mu t is relatively small. The data effectively collapsed onto a single line, as can be seen in this figure. Consequently, the measurements of the confined helium in the silicon cell could not support the finite size scaling theory. However, the superfluid density data of the confined helium in the silicon cell were analyzed using the effective confined size concept. Due to the excessive vortex that develops close to the silicon cell's SiO2 spacers, the confined size have been modified by this function, d plus 0.145. That value is due to the vortex, excessive vortex near SI2 spacers. So these effective confinement sizes successively collapse the sulfuric density data onto a single line. You can see here. Now let's see the specific heat of liquid helium confined in silicon cells. The AC calorimetry was used to measure the specific heat of liquid helium confined in silicon cells. The expression, there is finite size systems heat capacity, and there is bulk system, so specific heat difference is scaled by this function. So this expression scales the missing signal of the confined system's heat capacity. Here T0 is the reduced temperature that satisfies with chi T0 equal L relationship. The data of the heat capacity for the 4 different confinement sizes are given in the above figure. This figure. We can also to scale 1. We can also see that the data are clearly collapsed onto a single line. This line you can see here, single line. T is larger than critical temperature, and T less than critical temperature for bulk system. So you can see that the data are clearly collapsed onto a single line, indicating that the confined system's heat capacity data has been scaled by previously mentioned scaling function according to the finite size scaling theory. The figure shows the heat capacity for both T greater than T lambda and T greater than T lambda. Both case we can see the collapsed data. So this specific heat data confined in the silicon cells support the finite size scaling theory. Now let's see the sulfuric transition in two-dimensional helium film. It is not difficult to form an uniform film of the liquid helium that ranges in thickness from a few tenths to a few atomic layers. These thin films sulfuric transition occurs at a significantly lower temperature than the bulk system. The mechanism of the vortex unbinding provides the explanation of the for the sulfuric transition in this two-dimensional situation. In the figure, several physical properties of the two-dimensional liquid helium system are illustrated. The power law of the temperature with the nearly zero exponent is used to express the specific heat in the bulk system. So this bulk system. However, in a two-dimensional system, the heat capacity exhibits a peak above the transition temperature. You can see here. At the transition temperature, the sulfuric density in the three-dimensional system exhibits a power law behavior and drops to 0. Say, drop to 0 at T lambda. On the other hand, regardless of the film thickness, the values of sigma s over Tc for the sulfuric density in the two-dimensional system has the universal values of this value at the transition temperature or Tc. So a certain value here at the transition temperature here. So this value. The superheat density per unit area in this case is denoted by sigma s. This sigma s is the superheat density per unit area. This theoretical prediction was thoroughly tested by torsional oscillator measurements of the superheat density of thin films made on the mylar sheet up to a few atomic layers. Thermal conductivity in thin film exhibits exponential growth as well with temperature, while that in the three-dimensional system exhibits the power law of temperature behavior. This one. One more time. Thermal conductivity in thin film, this one, thin film, exhibits exponential growth with temperature, okay? While that in the three-dimensional system exhibits the power law of the temperature behavior. So that's different, right? This is so because heat in the three-dimensional system spreads by convection, but it transfers by diffusion in a two-dimensional system. So we can see the difference of the physical properties between two-dimensional system and three-dimensional systems. The superheat density of the thin films formed inside the porous quartz pores. That's the pores here, shown in the figure. This is the figure. The figure's straight line, this line, this black line, has a slope equal to the previously stated universal values of this value. The results of the experiment confirm the theoretical prediction. So different film thickness. We have the some values, superheat density values at the transition temperature, and if we connect these lines, then we can get the slope of this value. So this experiment result confirmed theoretical prediction. Now let's see the dimensional crossover. If the confinement is very uniform, the shift from 3 to 2 dimensions can be observed. The superheat density measurements of the liquid helium confined in the 0.519 micrometer silicon cell are shown in the figure. The dissipation of the torsional oscillator delta Q, this one, in this data specifies the dimensional crossover. Okay. One of the unique features of the two-dimensional liquid helium system is this peak in the dissipation. We didn't notice this behavior in any other silicon cells. The extraordinary uniform spacing between the two silicon wafers in this cell may be because of this. So this is the only observation of this kind of dimensional crossover so far. When the correlation length exceeds confinement size close to the transition temperature, the dimensional crossover occurs. For instance, liquid helium confined in a spherical pore with a diameter of the few tens of angstrom exhibits a three-dimensional behavior far from the transition temperature. The system exhibits a finite size effects. Nevertheless, when the correlation length gets closer to the confinement size of a few tens of angstrom near the transition temperature, the system exhibits the crossover behavior to zero dimension in this core system when the temperature is extremely close to the transition temperature and the correlation length increases to be more than the confinement size in all directions. However, it is highly challenging to contain liquid helium in a well-defined cylindrical column or sphere. The experiment involving helium confinement in a nuclear pore that is a cylindrical shape or aerosol that's a spherical shape has been carried out. However, the confinement was not sufficiently uniform to see the dimensional crossover. With the ferromagnetic films, we could see the dimensional crossover. However, we have to make the exceptionally well-defined confinement and regulate the temperature resolution to get close enough to the transition temperature in order to detect the dimensional crossover. So it is very hard to observe the dimensional crossover in the helium system or other systems. So this slide shows the dimensional crossover for confinement system. We can consider two systems, liquid helium system and the ferromagnetic material system. Liquid system, we can make thin film, and also we can have the complete confined system. For completely confined system, we have planar, cylindrical, or spherical system. And ferromagnetic material, we can have the thin film, that's planar, wire, dot, and the spherical powder. So in this system, we can observe crossover type to two-dimensional, just one-dimensional, cylindrical, one-dimensional, and spherical. Also, all direction is less than the correlation length. So that's we can see the crossover to zero dimension. And in the thin film, we have planar 2D and wire 1D and dot 0D. And the spherical powder system, also we can have the 0D crossover behavior.